Oh, it is 414. We did 411. F is a mapping of the two-dimensional disk to R2 continuous. Then either there exists x in D2 such that f of x is x, or there exist P1, P2 on S1 on the boundary, and lambda 1 greater than 1 and lambda 2 less than 1, such that f of P1 is lambda 1 P1, f of P2 is lambda 2 P2. So a strange kind of nonlinear eigenpoints. So if I have a mapping from a disk to the hole to the plane, then either there exists an eigenpoint or with eigenvalue 1 exactly in the disk, or there exist 2 points on the boundary of the disk with eigenvalue greater than 1 and eigenvalue smaller than 1. Smaller than 1, it could be negative. And let me simply repeat the proof, though I do not really need it. Last time I proved that either the first is true, or if the first is not true, then the first one, P1 and lambda 1, do exist. But I did not prove that P2 and lambda 2 exist. That's what was missing last time. Let me repeat it. Let me first introduce a function f, a mapping f tilde, which is simply f of x if f of x is in D2, and f of x over f of x if f of x is not in D2. It is easy to check that this mapping is continuous, simply because you check it, not a big deal. This mapping is continuous. You have to check it, but not a big deal. Then, as you easily understand, f is a mapping from D2 to D2, because this condition throws everything which happened to get out of D2 back into D2. And by the therefore there exists x in D2 such that f of x equals x. Fixed point theorem. But it is not f of x equals f, but rather f tilde of x equals x. I have to consider two conditions. First, x is in D2 inside the disk. Then f tilde of x, which is x, is also inside the disk. And therefore f tilde of x equals f of x. Because if f tilde of x is not f of x, then f tilde of x is on the boundary of the disk. These two functions are different only in this situation, correct? And then this f tilde of x is on the boundary of the disk, which is not the case. So In the first case, I've got what I wanted. In the first case, I've got this option. Is it clear?
If x is inside D2,
Yeah. Then x is f tilde of x. Then f tilde of x is inside D2.
f tilde.
No, look here only. Okay. But if f tilde of x is inside D2, it cannot be given by this formula.
Why is f tilde inside if x is inside? That's what
Because f tilde of x is x.
I mean, there
I'm
exists an
sorry.
x. Or
There exists an F. I'm sorry. Okay, yes. All right. Thank you.
Okay. Now second situation. X is in S1. That means x is always in D2, but maybe not on the boundary. But in this case, it is on the boundary. Then f tilde x is on the boundary. And there may be two situations. 2a, f of this x, is not in D2. Because it may be such a situation. But then f tilde of x is f of x over f of x, correct? And it is x. So I will get f of x is which is lambda, and since it is not in D2, lambda 1 greater than 1. The case 2b, f of x is still in D2. Actually, it is on S1 in this case. Is still in D2, but it is not. F of x is in D2. Then f tilde of x is f tilde of x, and it is f of x. And I have either option 1 or I have option 1 still. In this case, I have option 1. So either I have option 1 or first part of the option 2. Now let me show that actually the second part of the option is also realized. The second part of the option is also realized. I can consider two situations. First, there exists x in S1 such that f of x is 0. Could this happen? Yes. Then this x is a perfect candidate for P2. Lambda is 0, less than 1, and I'm done. So assume that for any x on S1, f of x is not 0. We have to assume only, consider only this option. Then. Consider for any x in S1, consider such a segment, x, f of x. Connect x and f of x. If it includes 0, then f of x is lambda x, lambda 2. Lambda 2 is negative. if x and f of x, okay, it is x, if this is f of x, and if 0 is somewhere here, then definitely f of x is x times a negative number. And I've got what I want. Yes?
I had thought that lambda 2 had to be positive.
No.
No.
No, it is simply not true. Last time I think Jean produced an example when this is not true. Consider the mapping which takes the circle, takes the, what is it, the disk and moves it far away.
Right.
Moves it far away.
Some lambda
Now,
less than 1. Right.
I have to assume that for any x in S1, x f of x does not include 0, because otherwise I know what to do. Does not include 0. But then we are in a situation of a dog on the leash theorem. X is me, f of x is my dog, and the interval never touches the origin. So if I go around the, what is it, around the hydrant, the dog goes with me, and my winding number and the dog's winding number are the same. But what is my winding number if I go around the hydrant? It is 1. So the dogs must be 1. So I get that the degree of f related to S1 is 1. But sorry, it is 0. Why? Because f is extended continuously to the whole disk. You see? It extends continuously on the whole disk, and we get a ready homotopy to a constant path whose winding number is 0.
You know, if you prove 1 is equal to 0 one more time.
It is my favorite theorem to prove. Now it is on equal ground with your proof. We're done.
So you just proved lambda 2 is always less than 0.
Yes, and that is the point. If they put here that lambda 2 is less or equal than 0, it would be, so the fact that it is less than 1 is actually misleading. It is misleading. Actually, I can insist that lambda 2 is less or equal than 0. Yes, you are right. Done. Isn't it?
Totally, except how did they miss that?
It is a misprint. Maybe it is simply a misprint.
Oh, it's still a true statement.
Yes, this is a true statement.
But I'm not in the habit of that sort of true statement.
It would be even more true if they put it that there exists lambda less than 1 over e. It would be an even more difficult problem to prove. Or say less than the constant of fine structure. Okay, are we done? Yes. Now there are a couple more problems that we better solve. 414 is done. I think we did 415. Did we do 416? I can show it. I can show 416 and 417. Don't get, it is not very strange that we are invoking the dog on the leash theorem so often. Frankly speaking, it is only our only tool. And if you have only one tool, you invoke it as often as possible. Okay, let me show problem number 416. F from S1 to R2 is continuous, and the winding number is not zero. Prove that every ray emanating from, it is easy, P meets F of S1. Again, I call my dog and it solves the problem. Assume the opposite. There exists, okay, first of all, I can easily assume that P is 0. Nobody objects. Okay? Assume the opposite. There exists a ray, lambda q, lambda positive, such that for any x in S1, f of x is not lambda q. Okay, oh, that's much easier. So there is a ray, okay? Let me introduce the angle variable in the complement of this ray. Can I introduce it uniquely? For example, I can always assume that this ray is angle 0, and for any point I can uniquely define this angle, and I do not have any chance to go around. Why? Because this, and all these points f of x are not on the ray, so the points of f of x do not touch this ray. Okay, so there is, outside of this ray, there is a global definition of an angle. Is it? If you cut the complex plane, then the argument, there is a unique, there is a choice of the argument outside of the plane, outside of the ray. Is it? Therefore, what is the winding number of this? It is the angle at the end minus the angle at the beginning, which is the same. Yes, because there is a global angle. And therefore the winding number is going to be 0. End of story. I wanted it to be a bit more complicated, but I failed. So the only thing, if there exists a ray which does not meet it, that means I take this ray and the whole curve is outside of this ray. Correct? And if the curve is outside of this ray, then on the plane outside of this ray, I can introduce global notion of an angle. And what is the winding number? It is the change of the angle. I do not have to go through splitting into small pieces because I have a global notion of the angle. End of story. And one problem more. Oh, 417. Last time we did 418. It is 418 is that in infinite dimension the ball does not have the fixed point property. It does have in any finite dimension, but not in infinite dimension. 417. F d2 to r2 is also continuous, and f of p dot p, it is dot product, is never 0 for any p in S1. Show there exists q in d2 such that f of q is 0. Actually, you could easily, okay. Okay. So, first proof. F of p dot p is either always positive for any p in S1 or negative for any p in S1, because if it is positive and negative, and this is obviously a continuous function, it has to take the intermediate value. Let us consider the first case. I can consider the second case by replacing f of p by minus f of p, which does not change anything. I am considering this case. The other case can be considered by replacing f of p by minus f of p. What does it mean? P. That means that f of p is on the same half plane. So I consider the half plane. I can connect p to 0 and consider the half plane. You understand what I mean, this half plane. And that means that f of p and p are in the same half plane. Therefore, this guy does not touch the origin. Okay? So, invoking the fifth amendment, which is the dog on the leash theorem, we immediately get what? That the degree of f on S1 is 1, simply. Because if I go around, I get winding number 1, so the winding number of f of p is also 1, f of p. And we already know that if degree is 1 and f is extendable to here, then it must take all values inside the circle. We already did it. Okay. So again, what I was surprised at, how much can we get from so simple object as a winding number. So far we're using only winding number, though the only problem is that we are staying in 2 dimensions mostly. Okay, so let me do 428. State and prove analog of the Borsuk-Ulam theorem for mappings from a circle to R. And consider mapping F from a circle to R. There exists P in circle such that f of p equals f of p star. It is really easy. It should be really easy. Certainly I have to assume the opposite. For any p in the circle, f of p is not... actually I can assume that p star is negative p. So the circle is centered in 0, so is not f of minus p. And I consider g of p equal to f of p minus f of minus p. F of p minus f of minus p. This is well defined and continuous. But look what we have. It is 1 by absolute value. Is it? It is 1 by absolute value. And therefore, it is either the value is 1 or negative 1. 1 or negative 1, always. The value is 1 or negative 1. But you see, the circle is connected. Therefore, the origin, the image must also be connected. I proved it once, that the image of a connected set under continuous mapping is connected. But 2 points is a disconnected set. Correct? So, this always must be either 1 or negative 1. Let us assume that it is always 1. It is always 1.
And g of minus p is equal to minus g of p.
Yes, and that is g of minus p is minus g of p, which is minus 1. Sorry, it can happen. If it is always 1, it cannot sometimes be minus 1. Done. Okay, and for 29, oh, but this is actually, I think it was already proven, I believe. If we have a continuous mapping between circles such that the f of that p and such that the antipodal points never get to the same point, then the degree must be non-zero, so f must be surjective. Surjectivity was already proven under this condition, but I think it is exactly what okay, it is a okay, I understand it. Got it. So it is 429. F is a mapping from a circle to a circle, continuous, and such that for any p on the circle, f of p is never f of p star. Okay. Okay, show that then degree, okay, it is easier. Degree f is not 0. Assume that degree f is 0. Assume that degree f is 0. Just a moment. Assume the opposite. Degree f is 0. Then just a moment, please. No, I wanted to do it that this is a mapping on, actually I can produce a mapping on the real line out of this, and I think this is true. And if it is a mapping on the real line, then by the version of the Borsuk-Ulam theorem that I have just proven, for some 2 points this must be true. And this condition, if degree is 0, it must mean that I can make a mapping on the line. Let me just.
That means there's a point that in the other circle that's never reached, and you can cut that circle.
No, it can be reached. I can go this way and then this way.
Can't you just take the angle?
In C prime, there's
Yes, I am thinking about this. Yes, actually we are doing this, the following. Under this condition, I can flatten the circle on a line, and then it comes into contradiction with the previous result.
What he said about C prime seems true. Why is that not true? You can't make the entire circle and then.
But you can do it this way. This and this, and you are covering everything. But actually,
Degree of f is 0. If you make this.
You have to do.
All the loops you do in one direction, you have to undo.
Undo the other.
Mhm.
Okay, that's fine.
Give me some time. Okay, let me just take a couple of minutes next time, because I feel that this is something very easy. I just cannot immediately get it. There is one thing more that I want just to attract your attention to. From this result, a very important thing is following from Borsuk-Ulam theorem. An important comment on the Borsuk-Ulam theorem. What does it say? Consider a continuous mapping of a sphere onto a plane. Any continuous mapping, whatever. Not onto, into a plane. Then there exists P such that f of P equals f of P star. In particular, it means that any mapping of a sphere, continuous mapping of a sphere to a plane, is not one-to-one. In particular, it means that this mapping is not one-to-one. There does not exist one-to-one continuous mappings from a sphere to a plane. And in particular, this proves that no piece of 3 or high dimensional space containing a ball can be homeomorphic to a piece of two-dimensional space. Because if I have a piece of 3-dimensional space and I can map it continuously and one-to-one to a plane, then its boundary is mapped one-to-one on the plane, which is impossible. And therefore, it is called the definition of dimension. Dimension is, in this case, dimension 2 is a topological invariant. dimension, actually any dimension is topological invariant, but dimension 2 is. But it is much more powerful result. There is no continuous mapping from a two-sphere to the plane. Simply there is no. Continuous one-to-one mapping, I'm sorry. One-to-one mapping from a sphere to a plane. A very powerful result. Now there is another result that I want to mention, and it is in, say, a consequence of Stone-Tukey-Delos sandwich theorem. And this theorem is due to Lusternik, Schnirelmann, and Borsuk. It is impossible to cover a sphere with 3 closed sets, none of which contains a pair of antipodal points. Try to cover our Earth with 3 closed sets. Yes, closed is important. None of which contains 2 antipodal points. You'll fail. If you replace 3 by 4, an easy exercise. How can I do it? Take the southern hemisphere and shrink it a little bit so it does not contain any, shrink it to the southern pole a little bit. I will cover almost all of the southern hemisphere. Then rotate it 90 degrees. Okay? Rotate it 90 degrees more. This, or actually rotate it 90 degrees and rotate it back a little bit. And then cover the remaining by the 4th. 4 is okay, but 3 is not. You cannot cover a sphere with 3 closed sets without antipodal points, but you can do it with 4. This leads to a, say, Lebesgue definition of dimension, by the way. Lebesgue definition of dimension is related to the fact how many sets do you have to cover everything. Okay, so how do I do this? Let me prove it. It's not a big deal to prove it. So you cannot cover a sphere with 3 closed subsets without an antipodal points. So assume the opposite. Sphere is K1, K2, K3. All of them are closed, and none of them contains antipodal points. Okay, consider f1 of x. Consider functions fi, from the sphere to reals. Fi of x is the distance from x to ki. The distance is well defined. The closest distance from x to a point ki. For example, if x is in ki, then fi of x is 0. These are obviously continuous functions. Easy exercise. Continuous functions on sphere. Now consider such g of x. It is f2 of x minus f1 of x, f3 of x minus f1 of x. It is a mapping from a sphere to R2. Continuous. Yes? A mapping from a sphere to R2, continuous. Then Borsuk-Ulam tell us that in this case there must be two antipodal points which have the same values. There exists P such that f2 of P minus f1 of P equals f2 of minus P minus f1 of minus P, and f3 of P minus f1 of P equals f3 of P of negative P minus f1 of negative P. Okay. P in sphere. But then P must be in one of these three guys. Okay? Let us assume that P is, say, in K1. It is in one of them. It doesn't matter which. It is easy to do it for anyone. Okay. Then P star is not minus P, I'm sorry, is not in K1. And from this it follows that f1 of P is 0. Better let me do it in K2, because I will show how to switch. f2 of P is 0. I'm sorry. Let it be in K2. It doesn't matter because I can easily redo it. Okay. Now see, what does it mean? It means that this is 0 minus f1 of P. It is obviously negative. f2 of P is 0. This is distance, negative. Correct? Equals f2 of P minus f of 2 of minus P, f minus f1 of minus P. And f2 of minus P is not 0, strictly positive. Okay, but there is something else. I'm sorry. I'm sorry. I screwed up and okay. So let P belong to Ki, then minus P does not belong to Ki, correct? But since minus P is also on the sphere, so minus P belongs to Kj, and therefore P does not belong to Kj. P and minus P must belong to two different guys. And now I know what to do. I'm sorry. I can write f I of P minus fj of P must be equal fi of minus P minus fj of minus P. From this it is true. Because if I subtract this from this, I will get the same, not for 2, 1, but 2, 3. By subtraction, I get the same for 2, 3. Okay? Now, fi of this is 0, isn't it? So I get and this is not 0, fj of P. Fj of P is not 0. Is equal to fi of minus P. Minus P does not belong here. So it is fi of minus P minus, what is fj of minus P? Minus P belongs to Kj, so this is 0. And this is strictly positive. 0 is strictly greater than 0, which happens but very rarely. End of story. So again, Borsuk-Ulam guarantee us that there will be such a point P. So we have point P and point minus P. P must be in one of them. Call this where it lives Ki. But since Ki cannot contain two antipodal points, then minus P is not in Ki. Okay. But minus P must also be somewhere in Kj. But because Kj does not contain antipodal points, then minus minus P, it is P, is not in Kj. Then this is true for this point, this is true. Look here. For any ij. This is true for any ij. But this is 0 and this is 0. And this is not 0, strictly positive, and this is strictly positive. Minus strictly positive is equal to positive strictly positive. Contradiction. Okay. A good exercise, but very easy. A unit ball, not a sphere, but a ball, is not the union of three closed sets, each with diameter less than 2. You cannot split a ball into three closed sets, each of diameter less than 2. Because if you split the ball, you split the sphere. Correct? And if the diameter is less than 2, they cannot contain, each pieces of the sphere cannot contain strict less than 2. They cannot contain opposite points. But then I can stretch these sets a little bit, just make it a little bigger, so that the diameter is still less than 2. Correct? But now they're covering everything. End of story.